Today we are reviewing the real number system, so fill that in the topic section of your notes sheet as well as today's date. Hopefully you just finished watching the introduction to the history of mathematics and seeing some different ways that people related to numbers and were able to organize their numbers. And so this is the foundation of how the real number system came about and how we were able to keep track of different pieces of information using numbers and a number system. So we're going to fill in this graphic organizer based on the real number system and the different groups that there are. So on your note sheet, I want you to fill in that all of the numbers that we're going to be working with this year are going to be real numbers. So we can go ahead and assume that everything we're working with, and there may be some instances where we'll discuss what non-real numbers look like or imaginary numbers, but for the most part we're going to be working with real numbers. So they're all going to fall in some of these categories. So after we have real numbers, we're splitting into two groups. They can either be rational numbers or we can have irrational numbers. So you notice that these are separate from one another. So they are one or the other. They're either rational or irrational. They can't be both rational and irrational. And we'll talk about the difference between those two in just a moment. If a number is real and it's irrational, then that's as far as it can be grouped. That's the least restrictive that it can be, is irrational. However, if a number is real and it's rational, it may also fit into some other subsets or in some other categories. So if it's rational, it may also be an integer, which may also be a whole number, and it may then be a natural number. But notice how these are kind of stacked inside, that all natural numbers are also whole numbers, and all whole numbers and natural numbers are also integers, and all of these numbers are also rational numbers. But a rational number does not have to be an integer, and an integer does not have to be a whole number, and a whole number doesn't have to be a natural number. So we're going to see what the difference between these groups of numbers are here in just a moment. I will tell you that there is a significant amount of writing that you are going to be filling in while the notes and the video is going on. So make sure that you pause at any moment that you need some extra time to copy down the notes. So the difference between a rational number and an irrational number. So like I said before, it can be one or the other. And so I've tried to, with this organizer, display the same information up here in words. So if a number is rational, that means that it can be expressed as a ratio of two integers. And so we're going to see some examples here in a little bit about what that really means. You'll also see that in the word rational, you can see the word ratio. And so a ratio is another word for a fraction. And so we'll see some of that in a little bit. Rational numbers as decimals, they always repeat or they terminate. Okay, and so we're going to see the difference over here. So they always repeat or they terminate. So they always have a pattern or they stop. Irrational numbers cannot be expressed as a ratio of two integers. So we're going to see some irrational numbers later that look like a ratio, but there's that key piece that says that it has to be two integers that form that ratio. As decimals, they never repeat or terminate. So that means that the decimals go on and on and on forever with no pattern. So some examples of irrational numbers would be the square root of 2, the square root of 3, and pi, because we see that as 3.14, but we also know that pi goes on and on forever with no pattern. One other thing about irrational numbers, if you see a square root, any number that is not a perfect square. So perfect squares being 1, the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3. So anything that is not a perfect square are going to be irrational under the radical. So continuing on, after we have our rational numbers, then we see that we have the group of integers. So remember that rational numbers may be integers if they fit in these categories. So integers, it says they are real numbers and rational numbers. So integers are all in all three groups. Integers are what we consider whole numbers and their opposites. And I put this after simplifying here, and when we work with classifying numbers, this part is going to be very important, that we can't just look at a number. We are going to have to make sure that we simplify it first before we can classify. But as far as integers goes, there are no decimals or fractions once we simplify that. So when you look at a number line, we know that we'll talk about our whole numbers here in a minute, but our integers are our negative values, including 0, and then our positive values, so 1, 2, and 3. So it's that whole numbers and their opposites. So if whole numbers doesn't mean a whole lot to you, hopefully it will in just a moment. So when we talk about whole numbers are real numbers, they are rational numbers, and they are integers. So whole numbers encompass all of those other subsets. So when we are talking about whole numbers, we cannot have any negatives, no decimals, and no fractions once we simplify. So we can kind of compare here the number line between integers and the number line of whole numbers. So when we restrict going down to the whole numbers, then it takes away those negatives. But we are still including the 0, the 1, the 2, and the 3 going on to positive infinity. And then looking at natural numbers, you may also hear those as counting numbers. So natural numbers are real numbers, they're rational numbers, they are integers, and they are whole numbers. So the difference between a natural number and a whole number is, and you can see this clearly with the number line, is that inclusion or exclusion of 0 when we're talking about natural numbers. So we include 0 when we're talking about whole numbers, but we exclude 0 when we're talking about natural numbers. So natural or counting numbers, when you start counting, you start with 1, 2, 3, 4, and so forth. When we're talking about whole numbers, we include 0. When we are talking about integers, it's our positive and negative whole numbers and their opposites. And going back up to rational numbers, then that's where we include our decimals that repeat or terminate and our fractions. So if you need a moment to finish copying this down, make sure that you pause the video. Okay, when we look at some numbers and we're trying to decide what sets of numbers apply to a given value, in this case we have negative 47, and so we're going to say, okay, is this an irrational or a rational number? Because we know it's going to be one of those two. Irrational numbers, we say that it cannot be written as a ratio of two integers. It would be a decimal that doesn't have a pattern and it never stops. So when we look at negative 47, one thing you might consider is, well, how would we write this as a ratio of two integers? And so if we think about negative 47, so when we're trying to write negative 47 as a ratio, we could write that as negative 47 over 1. So since we can write it as a ratio of two integers, meaning that negative 47 is an integer, as is 1, then that means that it would be a rational number. And so we know that then it can't be irrational if it's rational. So then we need to say, okay, is it any of these others? Is negative 47 an integer? And so we said that integers were whole numbers and their opposites, so that they did include negative values. It doesn't include decimals or fractions once simplified, and this is where that simplified piece comes in. So if we're talking about something that's simplified, this would be our simplified form, this negative 47. So we don't have any decimals, we don't have any fractions. Integers accept those negative values, so then this one would also be an integer. So now we need to see if this would be considered a whole number. Well, whole number said that we couldn't have any negatives. So right from there, we would know that it couldn't be whole. If it can't be whole, then it definitely can't be a natural/counting number. So in this case, negative 47 is a rational number, and it's also an integer. So it would fit in those two categories. Looking at the next one, if we had the square root of 36, and the rules say that we have to simplify first, so the square root of 36 is equal to 6. So we can't just look at seeing that radical and assume, oh, well, numbers with radicals are irrational. That's not always the case, so we have to pay attention and simplify first. So the square root of 36 is equivalent to 6. So this can be written as a ratio as 6 over 1. So that means it would be a rational number, so that it can't be irrational. So 6 would be considered an integer, so we would highlight that one. 6 is also a whole number, and it's also a natural/counting number. So in this case, the square root of 36 is rational, it's an integer, it is a whole number, and it is a natural number. Looking at the next one, we have 5.156849167 ... So we need to see if we can write this as a ratio. And in this case, it's impossible to write it as a ratio because it goes on forever and there is no pattern. So from there, we would know that it is irrational. If a number is irrational, it cannot be rational, it cannot be an integer, it cannot be a whole number, and it cannot be a natural number. So the only category besides being a real number is that it is irrational. If we had negative 213,000, we could write this as a ratio of negative 213,000 over 1. So then that would mean that this would be a rational number. And then we would need to see, is it an integer? Well, integers are whole numbers and they're opposite, so that includes those negative values. This is not a decimal, nor is it a fraction when it's simplified, so this one would also be an integer. And then we would need to see if it's a whole number. Well, remembering that whole numbers do not include negative values, so it cannot be a whole number, and therefore cannot be a natural number either. If we have 2.18 with the 8 repeating, we need to know if we can write it as a ratio of two integers. And these types of decimals can be tricky to write as fractions. Some of them are a little bit easier than others, but I'll just go ahead and write this one out so you can have it as a reference and try it out in your calculator. But it should be 197 over 90. Should, if you were to put that in your calculator, simplify to 2.18 with the 8 repeating, and at the end of your calculator it's going to round up that last digit to be a 9, so it doesn't mean that that 9 is really there, it's just meaning that it rounds that last digit because it ran out of room on the calculator screen. So maybe someday we'll talk about how to write repeating decimals as fractions, but at this point, as long as you can recognize that it is repeating because that bar is over that value, then that would already tell you right away without having to write it as a ratio that it is a rational number. So then we need to see if it is an integer. And we know that integers say that once they're simplified, you can't have any decimals or fractions. And there's no way to get rid of this decimal. The only time you would be able to remove the values after the decimal point is if they were 0. So in this case, the only category or set that this would belong to would be the rational number set. And looking at the last one, if we have 8 pi divided by 2, anything that you see with pi is automatically going to be irrational. So anything with pi is irrational. So I want you to look at the next set of these types of um, categories, and I want you to take a minute to fill these out and circle or highlight which categories or subsets you think each number belongs. So pause the video, and then in a moment I will go through each one of those and see if we agree. Okay, and looking at the rest of these problems, so we have the square root of 8 divided by 2. So if we were to put the square root of 8 in our calculator, it would give us a decimal that does not have a pattern, nor does it stop. So remember that I said earlier that any number that is not a perfect square, and 8 is not a perfect square, so it doesn't matter what else is going on within that value. If the square root of 8 or whatever that square root is, if that is not a whole number, then it's not going to simplify to be a rational number either. So in this case, it would be irrational. If it's irrational, it can't be anything else. Looking at the next one, so we have the square root of 81 divided by 3. So the square root of 81, 81 is a perfect square, so that would be 9. So we would have 9 divided by 3, and so we could simplify that to be 9 divided by 3 is 3. So we could write this as a ratio, so we can even see that 9 over 3 is a ratio, so it's a rational number. If we're looking at this, when we simplified it, 3 is an integer, it is whole, and it is a natural counting number. The next one, if we have 29 divided by 4, so if we were to divide 29 by 4, we would get 7 and 25 hundredths. So then we would be able to categorize this a little bit better. So we could see that it's already written as a ratio of two integers, so this would be a rational number. However, when we go further, we cannot have decimals with integers, so it cannot be an integer, a whole number, or a natural/counting number. So in this case, 29 divided by 4, 29 fourths is just a rational number. The square root of 18, 18 is not a perfect square, so it would be irrational. If it's irrational, it can't be anything else. 3.506. So we can see that this is a decimal that stops. So it doesn't matter how many digits it goes on, as long as it stops, it is a rational number. You could also write this how you read it. So we would read this as 3 and 506, and remember that this is the tenths, hundredths, and thousandths place. So you could write this as 3 and 506 thousandths. So it could be written as a ratio. And since it has a decimal, it cannot be an integer, nor a whole number, nor a natural number. Looking at 8.345,345,345 ... It is a decimal that goes on forever, but we can see that there is a pattern. So in looking at this 345 as our pattern that repeats, we could write that as 8.345 with a line over all those digits. So in that case, it would be a rational number. And it cannot be an integer or any of the other categories after that because of the decimal. Moving on, so we have 100 divided by 4. Well, 100 divided by 4, we need to simplify first. And so 4 goes into 100 25 times. So 25 is a ratio of over 1, so that would be a rational number. 25 is an integer. It is also a whole number, and it is a natural counting number. And looking at the next one, if we have the square root of 16 divided by negative 2, the square root of 16 would simplify to be 4. So we'd have 4 divided by negative 2, which would give us a value of negative 2. So when we are picking our categories, that's what we're going to base it off of. So this is a ratio of two integers here. 4 is an integer as well as negative 2, so it is a rational number. When we look here, we have an integer, but whole numbers do not include negatives. So in this case, this value would be a rational number and an integer. And then looking at 0. So 0 is a rational number. It is included as an integer, and it is a whole number, but it is not a natural number. So make sure that you have your notes filled out, and if you have any questions on any of these, please don't hesitate to ask. Your assignment is based on picking subsets and also coming up with your own values that correspond to certain subsets. So when you're finished taking notes and watching the video, then make sure to work on your assignment.